Hello, everybody. Welcome back. This is Dr. Gardner at the University of Montana. And today we're going to be talking about fluid discharge, flux, fluid flux, or Darcy flux, and Darcy's law. So these are how we think about fluid flow and quantifying fluid flow in the subsurface. So as always, grab your pen and pencil and get ready. So the first thing we'll talk about is fluid discharge. All right, and discharge generally denoted as big Q, and big Q is the flow, the volumetric or the volume of water that passes a plane per unit time. So this is length cubed per time. This is flow this is the volume of water per time. And it's important to remember that discharge, Q, is a vector. All right. It very much depends on, if we want to know the discharge, we really need to know across what the discharge is occurring. All right. And so we often denote discharge, or we think about discharge, for example, in a stream as the flow crossing the cross-sectional area of the stream. So there's some plane, and we have some discharge or fluid velocity vector. Actually, maybe it's better not to think of the discharge as a vector, but the fluid velocity as a vector. So we have some fluid velocity, v, which is a vector. So Q discharge is the flow across the plane. And if we have some fluid velocity, all right, randomly oriented compared to our plane, then what we're generally after is the component of that discharge that lies parallel to what we call the normal. And the normal is a n, the normal is a vector perpendicular or normal to our plane. And what we want this component of our velocity that falls parallel to n. And I'll denote that as v sub n. All right, and that is the normal, the velocity normal velocity perpendicular to the plane. Right? Just the velocity that crosses the plane. So we define the discharge as my V sub n dotted into the normal. Don't worry if you haven't taken vector calculus. All that means is it's the projection or the component of velocity parallel to the normal vector. All right, times the area A of our boundary. Right, and this is the normal velocity V sub n. Okay, so bottom line discharge is equal to V sub n times the area. And if we just do the units here, we'll get length over time times length squared, which is equal to length cubed over time. So that's good. That's the volume per unit time crossing our area. Okay, so discharge is the flow across our plane, and it depends upon the fluid velocity and its orientation with the plane. All right, so important thing is it is the entire volumetric discharge across this full plane. So Q is the volumetric flow across the entire plane A. All right. Another really useful quantity that we'll use a lot in groundwater is what we call the fluid flux. It also gets called the Darcy flux. All right, and we're going to denote that as little q, right? And little q, the fluid flux, is defined as the discharge divided by the area. All right, it is the amount of flow per unit area. So it's normalized, it's the discharge normalized by the area. Q is a vector. All right, so it has a direction and a magnitude. All right, and let's look at the units. Length cubed over time for discharge over area. So I'm just going to put that as 1 over length squared. All right. Length over time. All right. So discharge has the unit length over time. It looks like a velocity. All right. It looks like a velocity. Let's expand. It looks like a velocity, but it's not velocity. I'm going to say this. It's not the same as fluid velocity, even though it has similar units. All right. It is the discharge per unit area. And I'm going to show you why that is not equal to the fluid velocity, especially for us, well, for us in porous media. a plane in porous media. So let's consider a plane in porous media. So here's my plane A, but we're in porous media. So we've got grain sizes here, or grains. Okay. So, and here's our plane. All right. And it has grains and it's got let's say we're 100% saturated. So all of our pore space is full of water in this city. Okay. I want to know, I've got some fluid velocity sort of randomly oriented compared to my plane. Here's V, all right, and I want to know Q sub n, which is normal to my plane, and my plane is a plane in REV, and it has these dimensions of, we'll say the dimensions are delta y by delta z. All right, so I want to know what the fluid flux is across this plane. All right, and I've got some randomly oriented fluid velocity vector. All right, so the fluid flux by definition, Q sub n, all right, is equal to the discharge across my plane of REV, AREV. And AREV is given to us by delta y times delta z. All right. So this is my definition of flux. All right. It is the discharge per unit area. All right. Let me use this equation. I'm going to need to label it. We'll call this star. All right, so from star, I can say that my discharge now, Q, is equal to V dotted into N, my normal, all right? And then the area across which fluid can flow, all right? I can't flow fluid through sediment grains. So my discharge will only be across my void volume. All right, fluid can only flow across my void volume. So I get this V times the normal vector, n bar, times the area of my voids. So if I combine, let's call this double star. And star, I get Q sub n is equal to V dot n dot area of voids divided by area of REV. All right, I'm gonna make some simplifications. This is equal to V sub n, the component of my velocity across the plane. All right, V sub n. All right, times this ratio, area of voids over area REV. And this area, the ratio of these areas is equal to the porosity. So my discharge, Q sub n, is equal to my normal velocity times the porosity, n. Right, and this is an important relationship. It relates discharge and fluid velocity, or I'm sorry, flux and fluid velocity. It's important to note that the fluid flux or the discharge per unit area of REV is not equal to the fluid velocity. It is equal to the fluid velocity times the porosity. All right, let's think about the relationship here, or the relative magnitudes. If porosity is the ratio of the volume of voids to the total volume, porosity is always less than 1. In general, in porous medias, like a value like 0.3 is a reasonable sort of starting point for porosity. Right, so if I look at that, I say V sub n times 0.3, any number less than 1, the discharge or the fluid flux, the Darcy flux, will always be less than the fluid velocity, right? And that's because it is being normalized by a bigger area. Okay, so discharge is the total amount of fluid volumetrically flowing across a plane. Flux is the area normalized discharge, so it's the discharge per unit area. And it is basically equal to the velocity flowing across the plane times the porosity. All right, so now we're going to get to Darcy's law. And here we'll combine. Darcy's law is a very important relationship in groundwater, and I'm hoping this is review for you. But Darcy's law relates fluid energy or potential to discharge or flux. And most simply, Darcy's law can be written Q, and here I will use a subscript to indicate the direction of flow. So here, recall, discharge is a vector, and here I'm just going to consider discharge in one direction, the x direction. So I will use this subscript x. So Q sub x, all right, which is equal to the total discharge across the x plane, all right, normalized by the area, or the discharge per unit area in the x direction. And that is equal to negative k dH dx. All right, this is Darcy's law. Probably one of the more important relationships you will manipulate during this class. Very, very basic. And it relates the flux or the discharge. All we got to do is decide how we normalize by the area. All right. To the gradient in potential and the direction which we're interested in the flow. All right. So K is this relationship fudge factor, and it is called the hydraulic conductivity. All right. dH dx is the gradient of fluid potential in the direction of interest. All right, so this would be if the total vector Q is oriented randomly in XYZ place, we are only interested in the component of that discharge along the X direction. All right, then we only use the head gradient in the X direction. Let's look at units. Q, remember, is discharge per unit area. It's length over time. And recall this is equal to length cubed over time times 1 over length squared. All right, on this side of the equation, well, we have head, which is a length, over distance in the x direction, that's a length. I have length over length, so potential gradient in fluid potential, or the head gradient, is always a unitless number. And that tells me that K has to have the units of length over time. All right, so that implies K is length over time. All right, the next thing we're going to get to is this pesky negative. All right, and this negative just throws people for fits for a while, and so I think maybe the best way to try and tackle this problem is just to consider a head gradient. So let's say we're at the land surface here. I've got a couple wells. All right, and the water level here above a datum is given by H1, H2, and let's have this be X. And this is X equals to 0, and X is increasing. So let's have this be X equals to 10. And let's call this one 10 meters, and let's call this one 9 meters. All right, so let's just make so y negative k. All right, so let's make some observations or some general rules. One, we know that water has to flow from high head to low head. So water flows from high head to low head. So in that case, Q sub X will flow in the positive X direction. In this case. All right, because 10 meters is higher than 9 meters, the fluid flow is going to be in this direction, which is the positive X direction. All right, let's calculate head gradient. So remember these. So calculate delta H over delta X. So this is equal to 10 minus 9. And now the X where my head is equal to 10 is 0 meters minus the X where my head is equal to 9 meters is 10 meters. All right, and I'm going to get -1 meter. I'm sorry, this is a positive 1 meter. This is -10 meters. All right. So this is equal to -0.1. All right, that's my hydraulic gradient. So if I know Q sub X must be positive, so if it's going to be positive, then it is -K times -0.1 meters. And that will give me a positive Q sub X, right? So all the -K does is make sure -K ensures flow down gradient. All right. And by the way, K is always positive. Let's talk about K. So K is hydraulic conductivity. All right, and values for K are always positive. All right, that's a little confusing because I'm saying we call it -K times dH dx. The K here, the value of K is positive. The negative is -1 times K. Always positive. And it is a measure of the ease with which water flows through rock. or through our porous media. All right, remember it has units of length over time. Okay. K is equal to little k, we'll define it in a sec, rho water, G, which have the standard definitions, over mu sub water. And I'll define everything new that we haven't discussed here. So little k, and I put the cross through here just to be able to distinguish between big K and little k, is the intrinsic permeability of the rock. Oftentimes we just refer to it as permeability. All right. And the permeability is basically a measure of the properties of the pore network. All right. And it is ease of any fluid, ease with which any fluid could flow through the rock, right? It just is like how big are the pores? How well are they connected? All right. It is only a property of the rock. Oh, it's really messy. So this is a rock property. Okay. Rho water, well, that's the fluid density, that's water density. We know what that is. That's a property of the water. Mu sub W is the viscosity of water. All right, and viscosity is basically the resistance to shear of the water. Let's think about units of, do unit analysis and for our equation up here. So we know K has the units of length over time. We know that rho sub water, let's just break it out right now. So rho sub water is mass per length cubed. Gravity is length per time squared. All right, and viscosity is mass over length time. All right. So then what units are K? All right, so we got a length here length to the fourth here. So we are negative okay, I had to pause because I realized that I had made a mistake and I had to figure it out. All right, the units of viscosity are mass over length time, but viscosity in this equation is in the bottom. So I got to flip this. So this is length over time over mass. All right. So my masses cancel, T's cancel. And right now I have these guys canceling this. So right now I have a length, I have 1 over length time. So that in order to make this length over time, that implies that K is length squared. Because if K is length squared, then this guy and this guy go away and I end up with length over time. All right, so intrinsic permeability has units of length squared, right? And hydraulic conductivity, so big K length over time, little k length squared, right? And intrinsic permeability is the property of the rock that basically describes whether it's air or water or whatever, how well it can, any fluid could flow, all right? And hydraulic conductivity brings in these properties of the water, so the density and the viscosity of the water. So it includes these properties of the water, and it's really only valid then for water, whereas intrinsic permeability is valid for any fluid. Okay, so that is fluid flux, Darcy's law, and hydraulic conductivity and permeability. I hope you took good notes, and we'll talk to you later.